I'm going to talk about some joint work, emphasis on the joint aspect of this. But I'm the one that you get for this, so for better or worse. But I'm going to talk about optimal compilation for parametrized quantum circuits. This joint work with Tuomas, Laakkonen, Richie, Yeung, and John van Wetering. Okay, so quantum circuits, as everyone is very familiar with, is a kind of an assembly language of quantum computing. And something that we often want to do with quantum circuits is optimize them. So do the same circuit but with fewer gates. And the kind of old-fashioned way, I put this up as kind of a straw man because I don't know if anybody ever really did this, but the old-fashioned way of optimizing quantum circuits is to think about kinds of gate identities that we know and just apply them locally to try to get gates to cancel out. Right? So for instance, you might know that if I push a couple of Hadamard gates through a C0 gate, it flips around, right? So that's probably a rule that looks pretty familiar. And then a pair of C0 gates could cancel out. We get something a bit simpler, right? Well, you know, you can do this. A problem with this, though, is you start to think, well, what are my useful gate identities? And you come up with a few, and then a few more, and then a few more, a few more, and a few more. And you kind of wonder, you know, when will this end, right? I could actually put a line of like 20 slides of just pages and pages of this stuff. And it's part of the problem is that circuits are so rigid, right? So I need to come up with lots of different variations of essentially the same rule. But something that you can do that's a bit smarter than this is I can cut my gates open and get a much more flexible, essentially a graph type structure. And this thing's called a ZX diagram. So many people have probably seen this before. ZX diagrams are made of these small basic linear maps called spiders. This is always just a rank 2 matrix. It's got a 1 in the top left and an e to the I alpha in the bottom right. So you can think it's like a generalized phase gate. And it's enough to have 2 of these. So I have one with respect to the Z basis. I have one with respect to the X basis, wins the name, and they're related by a Hadamard gate. And now this thing, unlike a circuit, is a flexible object, meaning that if I deform this any way that I like, the linear operator it describes is always the same. Okay? And a useful thing about these objects is they satisfy a sequence of rules called the ZX calculus. And actually you can come up with very small, complete sets of rules for these diagrams. So for instance, these 1, 2, 3, 4, 5, 6 rules actually imply all of the true identities between ZX diagrams. So you sort of get a lot for not putting very much in. Okay, so if I go back to this example, I can cut my gates open and start to apply these rules. They're pretty simple to see how a machine would do this. Dots of the same color fused together. There's kind of a copy rule. Some more things fuse. Parallel edges fall off like this, and then, you know, at some point I'll get something much simpler. Right? So I could do this with circuit identities, but I'd need a lot of circuit identities. Here I think I use three or maybe 4 different ZX rules to do this whole reduction. Okay, so this is quite powerful. If we want to scale it up, we need to think about how to do this automatically. Right? And I guess the main, I should say we have a tool for this, automated reasoning with ZX diagrams. It's called PhysiX, pronounced like physics without the H. It's on GitHub. The main thing we use to automate this is we turn equations, which is like a 2-sided thing, into a rewrite rule. So we apply things in one direction. Okay, so this is a pretty good set of rules for working automatically with. And we can kind of massage this thing into a rewrite system. So one thing is obviously if I have a pair of dots, I should fuse them together. That gives me something simpler. This rule here, this is useful because you can see I've got 2 dots there and they get deleted, right? So that's useful. But how to deal with the color change? Something that you can do is you can say, well, you know, it's kind of annoying to have red dots and green dots, so let's just make everything green from the start. Okay, so that means put Hadamard gates everywhere. And you can see there's kind of 2 kinds of edges in these diagrams. I have edges that don't have Hadamard gates and edges that do have Hadamard gates. So rather than having, that's a little hard to see, rather than having one graph with 2 different kinds of nodes, I have one kind of node and 2 different kinds of edges. Okay. And if I do that, I can turn this into quite a useful, effective rewrite system. Okay, I did a little bit of magic there and generalized these two rules. So if you know about these kinds of things, this is called pivoting and that's called local complementation. But they're basically rules that I can use to delete nodes out of these diagrams. Okay, so now I just take these rules and I apply them as much as possible. It starts deleting nodes out of my diagram. At some point the rules don't apply anymore. I get a much simpler thing. Okay? And that's what happens here, right? So I can take a big circuit and I apply all these rules. And all of these rules essentially delete the kind of Clifford-like stuff in that diagram. So the things that came from Clifford gates, like C0, H, and S gates, go away. And the things that are left are things that come from non-Clifford gates. So this big circuit had a few T gates in it, and that's really what's left in this graph when we're done. Sort of one node for each of the T gates that was left in my circuit. And then we can try to extract this back out as a circuit. So if you're kind of careful about how you do this, you can always do this efficiently. So I'll just click through this. So here I took something that really didn't look like a circuit, and I can kind of move from the outputs to the inputs and sort of extract a circuit back out. Okay, so the first thing we applied this to was T-count reduction, and it works. Okay, so you apply this thing, you simplify, and in the process, a lot of things which came from these non-Clifford gates kind of find each other and either combine to make something that's Clifford, or they cancel out to make something trivial, and you can get a circuit with fewer T gates. Okay, so in this case, I think there's something like 6 fewer T gates from the top to the bottom there. I know it's a little bit small. So we released this in, I believe it was March of 2019, and then a kind of a weird thing happened, which is another paper came out by Zhang and Chen at Alibaba, also in March of 2019, and they used the same benchmark circuits as us. I know it's very tiny, and they got the same exact T counts as us. Okay, so they did something that looks totally different from what we did, but they got exactly the same results. I remember a panicked email coming from them when they saw this paper on the archive, and they said, "Oh, we got exactly the same results. What's going on?" We're like, we don't know. But we thought about this for a while, and a possible answer is that even though these techniques look quite different, maybe they're actually the same thing, kind of, up to isomorphism. And this could be the case. So the main rule that we use for eliminating T gates is this thing called gadget fusion, which is we have these particular shapes of diagrams, which we call phase gadgets. It's like an unlabeled node connected to a labeled node. And if a pair of these is connected to the same nodes, they sort of merge together and their angles add. So if both of those were like T gates, they could cancel out with each other. If you know about things like phase folding you might have encountered if you do work in this space, or if I have Pauli exponentials, how their phases can add together and cancel out. This is sort of the same concept, but kind of witnessed as a ZX diagram. And actually, so Will Simmons, also at Oxford, wrote a paper relating sort of the ZX moves to the corresponding sort of phase folding moves. And it does look like these are the same thing, but the argument is quite complicated, and it's kind of depends on really exactly how you implemented this algorithm, whether you're going to get the same results. So another possible answer is maybe we actually just both did as good as possible, right? So maybe we both got the optimal T counts, right? Seems unlikely. I see people who know about this making a face when I say that. The reason that this is unlikely is both of our methods are efficient. They're polytime. Whereas we know even for diagonal circuits, T-count minimization is equivalent to this known hard problem, which is a least distance decoding for Reed-Muller codes. Well, okay, highly believed to be hard problem. Okay, so we don't believe that we did this efficient thing and then we actually got the exact optimal T counts. That seems unlikely. But what if what we're doing is not actually t-count minimization? Okay, so our procedure knows about Clifford gates, and it does something special with Clifford gates. But the way it treats t-gates, it doesn't really look at the angle. Okay, so this works just as well for any parameters here. They don't need to be kind of t-like. So in ZX diagrams, a t-gate makes a pi by 4 parameter here. It doesn't need to be pi by 4. It could be anything. So it's really dealing parametrically with these gates. And the same thing happens with phase folding and sort of phase polynomial stuff. So phases are kind of treated as black boxes, or at least the non-Clifford phases are treated as black boxes. In other words, they're treated as free parameters. So the same optimization would happen for any choice. Those didn't have to be t-gates. They could be any other parameter. I would have gotten the same number of them coming out at the end. So maybe what we're doing is not t optimization, but parameter optimization. So we can try to formalize this. So a parametrized circuit consists of gates from a discrete set and then also parameterized gates. So things which are functions of some input parameters. So I can think of these as functions from a parameter space into the space of unitaries. And we say that a parametrized circuit reduces to another parametrized circuit if there exists some function on my parameter space such that C1 of this set of parameters equals up to a global phase C2 of that set of parameters. Okay, so this is a reasonable notion of what it means for two parameterized circuits to be equal to each other. And we could say, well, maybe we don't want to consider all the functions. Maybe we want to consider a class of functions. And I'll say a little bit more about this class right at the end. But something we notice is all we ever really do is we just add parameters together. That's the only thing that decreases parameters. So maybe I should just consider circuits which are affine functions. So the new parameters are affine functions of the old parameters. And then I can say that C1 affinely reduces in that case. And also, something that it crucially uses is that parameters never get copied during this process. So I don't have an alpha on my left that becomes two copies of alpha on the right. So we can restrict this farther, and we can say, okay, well, first of all, we think that's hard if we actually copy parameters. We have some evidence for that. We can say that an affine reduction is parsimonious if it doesn't make copies of parameters. Okay, so this is just saying what that affine function is that's not copying parameters. And now you can say, you can define the problem, affine unique param count. We're given a parameterized circuit on a parameter space and an integer L. Decide if there exists a reduction to something of size L. Okay, so this is the decision problem associated with parameter minimization. I say, is there something that has this many parameters? And the theorem is, this can be efficiently and constructively solved. This can be decided. And the way you decide this is you actually just run physics. Okay, and it will tell you the minimum parameter count. Okay, so if I put Clifford's in, and then everywhere I have something non-Clifford, I just put a free parameter, and I run exactly the algorithm from the 2019 paper, it does get the optimal parameter count. It's quite surprising. It's almost telling you that actually there is nothing better that we can do than just the super naive thing. Okay, so how do we do this? We, this is basically just saying, what do? We run physics. And then this thing has the optimal parameter count. I think I'll have I'm quite near the end, so I've got a bit of a proof sketch here, but maybe I'll just kind of jump past that. A key point is that you can you can pull out all the non-Clifford stuff, and this thing becomes a stabilizer state connected to its non-Clifford stuff. And then you can reason about the stabilizers of that state to say, well, actually, there are no more reductions than the ones that physics knows about. Okay, so anyway, the paper's coming soon if you're interested in the details there. A couple of things that we're looking at now is kind of how necessary these assumptions are. So the affine assumption is actually not as strong as it seems. If you assume that the function is analytic, this actually implies that it has to be affine. So there are actually no non-affine analytic functions of parameters which result in genuine circuit equations. However, it doesn't, this thing, the sort of Euler rule, the thing that completes the ZX calculus, it's only piecewise affine, so it wouldn't apply to that rule. That rule doesn't count. And this parsimonious thing is kind of annoying, right? It seems less easy to justify. Now we have a proof that if you copy parameters and you do this and you ask the parameter minimization problem for ZX diagrams, which is the same as asking for post-selected circuits, that this problem is NP hard. So you can encode SAT if you do it with ZX diagrams. Probably there's a way to do this with circuits already, with unitary circuits, but we don't know how to do it yet. Okay, so those are the two big open problems. I mean, the title of this sounded like, hey, great news, we have a way to get optimal parameter counts. But the bad news is there's nothing better than what we've already come up with for minimizing parameters for circuits. So there's kind of two ways to see this. Anyway, if you want to see the paper, we tried to get it on archive by today, didn't quite make it. But it should be out next week. Yeah, thanks.
Thanks, Alex. Questions? Okay, I've got some. Can you explain a bit what is the actual restriction on the parameters? Like, they're unique, or like they occur once?
Yeah, so you can imagine that, so I have this parametrized circuit which takes a vector of parameters to a circuit. Now I'm rewriting that to another parametrized circuit. It can take a vector of a different length, so with fewer parameters, to a circuit. And you're asking what is the function from, r to the k to r to the l. And then you put a restriction on that function, and we say, well, it needs to be an affine function. But this parsimonious restriction is actually saying that there's only a non-zero entry in each column, one non-zero entry in each column of the matrix. And this sort of corresponds to one usage of the parameter from the left-hand side on the right-hand side.
Okay, but the parameters themselves can occur arbitrarily many times in the diagram.
No, because the length of the tuple is the number of parametrized nodes.
Right.
So it doesn't let you copy parameters.
Okay, so an interesting thing, which I'm going to not get right, is that for a parameterized circuit which doesn't have many parameters, this has a simple representation in Fourier space. It makes it easy to simulate.
Okay. Interesting.
Any other questions?
Yeah.
Mark?
So your parameterized gate is just the Z phase gate, right? And does the proof pretty much depend on this? But if you were to go to like a controlled rotation gate or something like this, does it still work?
Annoyingly, no, because the ZX diagram of a controlled rotation gate uses that parameter 3 times.
Yeah, that's what I'm asking.
Right. So it could be a strategy like this will work for controlled rotation gates, but yeah, it seems very somehow representation dependent. There is some representation dependency in this proof. It's really something to do with the fact that we're using ZX diagrams. So,
right.
But it'd be good if we could talk about those, because those are used in VQCs all the time. So.
Yeah. Thanks.
Just a curiosity, in the definition of a affine function, you said that the matrix is composed of integers to mix the parameters.
They don't need, you don't need to assume that they're integers, but actually once you have one of these parsimonious reductions, it happens to be that the only possible coefficients are +1 or -1.
Ah, okay.
So that follows.
Okay, thank you.
Okay, well in that case, let's thank Alex for the talk.